Good afternoon, students. Now let us continue with the carbohydrate chemistry, where in the previous class we have discussed about the structure of glucose, and now we are going to compare the structure of D glyceraldehyde with D glucose, and we will see what is the significance of the term capital D in glucose. Okay. Now let us start with the structure of glucose. This is CHO. So again it goes like this. So this is the structure of D-glucose, right? And this was the structure of D-glyceraldehyde. And let us now compare. Okay, if we consider this segment, this is the CHO part, which is the CHO part here, right? If we consider this part, CHOH, CH2OH, so this is the thing, right? Now, as we have discussed in the other class, that D-glyceraldehyde is the smallest possible carbohydrate molecule. So, a carbohydrate molecule will have these groups, right, which are present in D-glyceraldehyde. Only with the case of the aldehyde, in some cases it can be ketonic carbonyl also, right. Now, if we compare, so glyceraldehyde is the mother form or the basic form. Okay, there 3 carbons are there, but in glucose how many carbons are there? In glucose 6 carbons are there. So from D-glyceraldehyde, if we go on increasing a unit like this, suppose first we are adding one CHOH, then we are going for another CHOH, then so gradually on adding each carbon with the side groups H and OH, so we are getting glucose. Okay, so we can say that from glyceraldehyde, by adding these carbon atoms we can get glucose, and we can also move to higher analogues, right. Now if we compare, okay, in D-glyceraldehyde what was the case? This OH group is on right hand side, this one is on right hand side. Here also OH is on the right hand side. So since this was D, so this will also be the D1, right. So how do we specify that? Why this is D-glucose? This is simply because of the reason that the OH group on 5th carbon, let us name the carbons, rather number the carbons. So on the 5th carbon, since the OH group is on the right hand side, it is D-glucose, right. Similarly, what will be the case for L-glucose? Okay, we have seen that it is nothing but the mirror image of D-glucose. So it's very much like this, CHO. So on the 5th carbon, OH group is on the left hand side. Since OH group is on the left hand side, it is nothing but a L-glucose, right. Now, so overall, if we have a look at the structure of glucose, what we can say, the first thing is, the first point is, it's a 6 carbon chain. So it's a 6 carbon member, right. Next thing, it has an aldehyde group. Next, third thing, it has 5 alcoholic OH groups. Now, out of those 5 alcoholic OH groups, one primary alcoholic OH is there, and 4 secondary alcoholic OH groups are there, right? So this is all about the structure. Now let us proceed with some reactions which will prove that okay, these entities are there in the structure of glucose, rather in the chain form of glucose, right? So let us start with the first point. Okay, what's the first point? The first point says that it's a 6 carbon member, right? So if we take glucose, now we are representing glucose like this. Now if we take glucose and we heat it with HI, so what's the result? The result is nothing but like this. So this product is nothing but an N-hexane. So this proves that glucose molecule is having 6 carbon atoms in its chain. That is, it's a 6 carbon member, right? This is the first one. Now what was the second point about the structure? The second point about the structure is it contains a free aldehyde group. Okay, so since it has a aldehyde group, or rather a carbonyl group, okay, so it's going to suffice these two reactions. So if we consider glucose, so we all know that to any carbonyl compound, if we are going to add HCN, so via nucleophilic addition reaction, what will happen? We all know that in carbonyl group, this is delta plus and this is delta minus, and if we have HCN, that's going to generate H plus and Cn minus. So Cn minus will link to carbon and H plus with O, and the resultant form will be something like this, which is nothing but a cyanohydrine form. Right? So we are getting this cyanohydrine. So this cyanohydrine formation proves that glucose is having a carbonyl group, and that too, since it's a terminal one, it's an aldehyde group, right? Now there's another reaction which can prove that carbonyl group is present. The other one is, again we are taking a glucose unit, and we are treating that with hydroxylamine. This is hydroxylamine. So what happens when hydroxylamine reacts with glucose? It gives rise to the formation of this thing. Okay. So what is this form? We have started with the carbonyl C double bond O. Now we are getting C double bond NOH. This is nothing but an oxime. So this oxime formation also proves that a carbonyl group is present in glucose, right? Now what about the third one? The third form was that glucose is, the third point about the structure was, the glucose is having 5 alcoholic OH groups, okay, where we have seen that okay, 4 are secondary alcoholic OH, 1 is primary, but what about the main thing? It's having 5 alcoholic OH groups. So if we take glucose and we are going to treat this with acetic anhydride. Now we have seen this reaction. You take any alcohol that or a phenol, which is having an alcoholic OH group, you treat that with acetic anhydride. So H will be replaced by COCH3 of alcoholic OH. Okay, H will be replaced by COCH3, right? So that is nothing but introduction of that COCH3 group, that means acetyl group, is known as acetylation reaction. Okay, so here we are going to get that only. So OH becomes OCOCH3. This is the acetyl group. So this is nothing but, this compound is known as, so 5 acetyl groups are introduced such that this product is nothing but glucose pentaacetate. Right? Now, what about the next point? It's having one primary alcoholic OH group and it's having 5 secondary alcoholic OH groups. Now, we have already learned in alcohols and phenols that primary alcohol on mild oxidation gets converted to aldehyde, which on oxidation gives a carboxylic acid. But a primary alcohol can give rise to a carboxylic acid directly without going through the aldehyde stage. Okay, so if we use strong and drastic oxidizing agents, right? But a switchover or an oxidation from an aldehyde to a carboxylic acid can be achieved by mild oxidizing agents also. And if we have secondary alcoholic OH groups, that on oxidation can give a ketone, but ketone on oxidation is not going to give carboxylic acid easily. We need to use drastic or strong oxidizing agents. We need to employ high temperature and pressure. Then also we will not get a carboxylic acid having the same number of carbon atoms. Okay, that will, the main ketone is going to undergo fragmentation and it's going to give a large number of, a mixture of carboxylic acids, each with the number of carbon atoms which is less than the parent ketone, right? So let us take a carbohydrate molecule. If we treat this with a mild oxidizing agent like bromine water, it's a mild oxidizing agent. So if we are giving a mild oxidizing agent, so that's going to oxidize what? The aldehyde group. That's not capable of oxidizing the alcoholic OH groups. Okay, so we are getting this. CHO is getting converted to COH. So this compound is nothing but a gluconic acid. Right. Similarly, to this, if we are going to give concentrated nitric acid, so concentrated nitric acid means it's a strong, capable oxidizing agent. So it will not only oxidize aldehyde to carboxylic acid, but it's also going to oxidize the primary alcoholic OH to carboxylic acid. But no question of oxidation of secondary alcoholic OH to carboxylic acid is possible. Okay, so here we are getting this one. Sorry, so the primary alcoholic OH group is also getting converted to carboxylic acid. So this is nothing but, this is saccharic acid. Okay, sorry, there's a wrong in the spelling. This is saccharic acid. Now, if we have gluconic acid, to that also if we are going to add this concentrated nitric acid, then also we will get saccharic acid only. Okay, so these reactions prove the structure of the chain form of glucose.